Okay, welcome back. This is a new unit now, and unfortunately, unless I've been able to work out something downstairs with the office, I may or may not have been able to get you the packets for atmospheric energy and for meteorology. Now, if I wasn't able to get you those packets, which for the present time of this video are in this room, I would like to walk you through how to find your digital resources after visiting Google Classroom, going to my posts, and clicking the link that leads you to the parent-student portal. Okay, you can choose either the Chinese and English, or you could just choose whichever one works best for you. For our lessons, I'm going to continue to instruct them in English, but you can follow along with the translated versions if you'd like. Within the parent portal folders, you will see that we have our language folders. We have our reference tables in case you need them. Okay. Within the English or the Chinese, you'll find that there is an atmospheric energy folder. You're going to open up that atmospheric energy folder, and if you need the notes, you are scanning to see which one of these says ESN 6. Okay? This is a set of notes that you're going to want to either put in a new tab, if you have the opportunity to maybe print them out. I know that paper is going to be a very limited resource for some of you, and I do apologize, because I hope I can get those copies to you before the end of this week or when you're coming to pick up your computer resources. But if you don't, make sure that you're using maybe a notebook, or you have some other source of paper that you can take notes off to the side when doing these things. I know that you're not necessarily going to be able to label all the diagrams. You may need to make your own sketches and fill those diagrams in appropriately. Now, back to here. If I refer to any labs, access points, or practice documents, you're going to be going into these folders as well, and for this unit it will be this specific folder of these folders. And our first one, so that you know which one we're going to be using, we have ESN 6 as our notes. We will be using the Convection, Conduction, Radiation, Independent Practice. And I think this is the document right here. So it says copy of Convection, Conduction, Independent Practice. This is a document we will be using after we're through with the notes. Now, if you need access points, this should be the access points, where you can have the ability to read through if you need an extra hint or help as you're checking your answers. And if you need them, or when you need them, the answer keys are available here as well. For all of the folders practice is in one document for the answer key, so you will have to scroll through. All right, let's get started. So in order for us to start this thing off, atmospheric energy, we're not quite in meteorology. We have to understand some key components of how energy moves through multiple systems. That could be any of our three states of matter, solid, liquid, or gas. We may also be talking just in terms of the entire universe and how energy moves. So to start us off, the first one I want to talk about is convection. Convection is going to be our first transfer of energy. We've talked a lot about convection. We've seen convection during primarily density. We saw it during plate tectonics, and now it's going to rear its head again back to talk about transfer for all fluids. Okay? So this gets us kind of into the mindset of now thinking about air when we eventually get to meteorology. So any fluid has the ability to heat up, and that hot air, if we remember our density hand, so you may not have to go along with me anymore because I can't see you, but neutral position. Okay, we've got our two fists. They're going to represent our matter, okay, our stuff. And when we heat stuff up, that stuff doesn't like to stay close to each other, so it likes to spread out, okay? And maybe if you remember that next step, if it spreads out, it's less packed, which makes it less dense. And typically, if it's less dense than the surrounding environment, that material will start to rise up, okay? So that's going to be the beginning of our convection cell. We've got material that is less dense, due to it being heated, less packed, less dense, tends to rise compared to its environmental conditions. Okay? Now, as it rises up, it may hit some sort of ceiling, natural ceiling. It may not actually be a ceiling like the classroom, but it might be a place where it's exhausted its heat, it's been pulled out, and it starts to cool off. And as it's moving to those outside regions will start to cool down. Those molecules start getting closer together again. They become more packed, more dense, and compared again to the surrounding environment. If it's more dense in that environment, it starts to sink down. Now, if we think about it, if we're removing material here, we need to fill that material back in, and that's what that cold or cool, more dense material does. It fills right back in towards that heat source, and that whole process begins to cycle around and around. Okay? So, if that's something you like to practice, feel free to pause, run through that, rewind it, whatever helps you. All right, so here let's talk about convection through a fluid. So we've got a heat source here in our pot on the stove. We've got flame. That flame is heating up this fluid inside, which is water. That fluid, that gets heated up with more energy. It decreases in its density, rises to the top. The artificial ceiling here is the top of the water layer. It moves out to the sides, cools down, becomes more dense, sinks, and fills back into the heat source. So label up, if you can, heat source, convection cell, and the water is what is called a heat sink. It is the material that is able to absorb heat energy in order to complete this cycle. All right, so convection and gas works very similar. We've got a bedroom with a radiator, which many of you may be familiar with. That is our heat source. Okay? The walls, the window, the floor, they're all heat sinks. Okay? So this whole area out here is the heat sink, HS, I'm going to move it over here, HSINK. This is going to be HSOURCE. Woo! You can tell I've been doing a few of these videos this morning. All right, so heats up the air, air rises because it's less dense than the environment around it. Hits literally a ceiling. That ceiling starts to absorb or take that heat away as the heat sink, and it starts to cool down, sinks, and fills back in. Okay? That's why when you intend to put your hand over a radiator, if you feel the heat for two reasons. We'll learn about radiation, but you feel some of that warm air that's being heated up passing over your hand. So what I'd like you to do, pause the video, try answering these questions. These are nice notes, questions for you to recap what I was just saying here. All right. Conduction. Conduction is another transfer of energy, but this time it's through a solid. So when we go and we touch our face, depending on if you just came from outside or if you've been inside for a while, maybe your face is kind of on the cooler side and your hands are warm. Or it's the opposite. For me right now, my face is cold and my hands are warm. So therefore, the heat is conducting. Now, how is it conducting? What process is it going through? Let me take my hands off my silly face. If my hands are hot, the heat from my hands transferring into my cooler face. My cooler face is the heat sink. So the hand would be the source in this case, and the sink would be my face. Now, if your hands are cold, I'll have to edit this one maybe.
Good morning, UNHS. This is just your morning reminder to wash your hands. It is 9:20. This is a public service announcement. If you have not washed your hands by the time you have been in the building, now is a good time to do so. Please give me a call at extension 3021 if you have any questions about your morning or if you have anything that you need troubleshooting. Thanks so much.
Okay, back from that commercial break. Honestly, I'm not even going to edit this because I don't have time to do that. So here we go. Conduction. We're talking about a solid surface touching another solid surface, and that transfer of energy moves through from your hand to your face. If it was a table that was cold, put your hand on the table, and you will feel the table is probably colder than your hand. Therefore, the heat is being extracted from your hand into the table. All right. Now, this happens more efficiently because we actually have molecules touching molecules. All right? Now, big indicator here. All the energy of the universe always flows from high to low. Like how I did that. All right, so it all flows from high to low. Now here I labeled the heat source. I labeled this just S, so I'm going to add the OURCE to this. Our heat sink is the bar, and as this illustration is trying to provide to you is that it's hot here and it's transferring over. And you can see that the transfer is occurring because there's a slight difference in the thermometers as this heat eventually makes its way out to the furthest thermometer on the right. Okay, given an opportunity, try to answer those questions to accentuate your notes. Okay, they're good little checkpoint questions for you. All right, let's move on. So let's talk about this little setup here. This is called a calorimeter. Okay, we're not necessarily going to have calorimeters to work with hands-on because of the circumstances, but let's just analyze what they are. So these dark lines going around, that is a styrofoam sealed cup. So we've got two styrofoam sealed cups here. We have an aluminum bar that separates the two of them but connects inside of the fluids that are in these cups. Now, this cup here is starting at a colder temperature. This cup here is starting at a warmer temperature. And over time, we will see how these thermometers will adjust from a heat source to a heat sink, because we do have a metal bar here for conduction to occur. Okay? So I think what's important to realize is that we have high energy, low energy. So the expectation, if you take a moment to hypothesize, what do you think will happen to the direction, or what direction do you think the heat will move due to the current setup? So pause, think about that for a moment, ponder. Okay, so if you had a moment to actually think about that, you're going to go from high energy to low energy. So the flow, if I stop touching the board, the flow will move to the left in this diagram because you have a higher heat source here. One thing to point out is we may lose some heat from the bar due to our next form of heat transfer, radiation. So it may not be perfect. The amount lost here may not be perfectly gained here. Okay? If you'd like, you can try to sketch out a graph here. So radiation, let's get to our last one. Radiation is the transfer of energy without the use of a medium. A medium means we do not have material. There's no matter in between the source and the sink. Okay? I know this sounds complicated. It sounds like magic. Okay? In a way, science can be magical. So this is exactly how all the sun's energy comes from that giant ball, on average 93 million miles away, to us here at Earth. Okay? Now that radiation transfers as light, electromagnetic energy, which we'll eventually be learning about before we get in deep to astronomy. But all of that transfers due to radiation. Once it hits the surface here and we absorb that radiation, we can then go through the process of either conduction or convection, depending on what that radiation has warmed up here on Earth. Okay? So if the sun heats up the ocean water may start to go through some convection. If it heats up the ground, it may cause the air to have some convection. Okay? If I'm warmed up by the sun and then I touch someone else who is in the shade, I may be conducting the energy I absorbed due to radiation of the sun. Okay? So let's talk about how different surfaces have different impacts on how much is absorbed or reflected. So if we're talking about two ideal situations, one where we perfectly reflect versus one that we're perfectly absorbing, the following conditions will be necessary. So under perfect reflection conditions, we want a light color surface. Light color surface. We want it to be smooth. Woo, smooth. Good job, Mr. Ryan. Smooth. In order for this stuff to hit and reflect. Now, if we wanted to absorb energy, we want it to be a dark color. Okay? And we also want the surface to be rough. So let's explain. Now maybe a light color surface, you can think of things like snow, a white t-shirt, white paint on a house, or the roofs within the city as we try to reflect radiation back into space. Or you can start to think about over here for the cases where you have more absorption. Think about like a dark jacket in the winter, or maybe the pavement or the road surface in the summertime. Those dark surfaces versus those light surfaces have drastic differences in how much they absorb and reflect. So a perfect example, a white painted rooftop is going to be smooth and flat to help reflect light. A pavement might be bumpy and dark in color, and it will absorb more. The idea for absorbing more because of the texture is because as that light comes in and it bounces off these little ridges, it doesn't have a perfect pathway to get out, so it bounces into itself some more, and more gets absorbed. A couple of good questions here for you to ask yourself. Talk about things like the black sands in Hawaii versus the light-colored sands in the Rockaways. Which do you think will be hotter and why? Also, parking lots versus maybe a grassy park. Maybe if you're in Central Park and you're walking on the sidewalk with bare feet and then you jump into the grass, you'll notice the temperature difference because of their makeup. All right. So we have a little bit of practice embedded in the notes if you'd like to do them. If you don't, feel free to jump into checking out the guide practice questions before I get there, or fast forward this video to the point at which I'm going over the guide practice questions. But if you'd like to, let's try these out together. So we've got a light bulb. It's an old incandescent light bulb. That means this little filament here heats up to give off light, and that light is hitting both of these cans. So we've got a shiny can and a dark can. Okay, just like we're talking about different colored surfaces. And we have light, which emits radiation. Okay? They are equal distant apart. The light bulb is turned on for the same amount of time, and both of them have insulated lids with those inserted thermometers. What you want to do is read through these questions, attempt to answer them on your own. Feel free to pause now, challenge yourself to these questions, and then we'll come right back. And we're back. Okay, no, I can't. Oh man, YouTube's gonna. Oh god, I used Baby Shark. All right, here we go. So label on the heat source. We got the heat source here, the light. Okay. What is the starting temperature at each of these in the experiment? So it looks to me like it's about 40 degrees C, a little on the warm side. Okay. Which should heat up faster and why? The dark can should heat up faster. Whoop, dark can. My board is misbehaving. I'm not done with that answer. So if you just left dark can, you have to explain why. Briefly, you should add to this. I'm going to try to save some time in the video every now and then. But the dark can, it's darker in color. It's black. It's going to absorb more radiation. That's why it's going to heat up faster. Which can should cool off faster? Well, chances are, if we end up having the shiny can not taking on as much heat, it should, if they're made of the same material, if they're made of the same metal, these cans, the shiny one should cool off faster because it didn't gain as much. Okay, because the shiny can reflected most of its energy. Here's the why. It reflected most of its energy, so when it was time to cool down, it didn't have to lose as much heat as the dark can did. Okay. What is this experiment trying to prove? What's the topic? The topic is radiation. So radiation is what it's trying to prove. And how that radiation is affected based on the color of the samples. All right, so why is it important to keep light source equidistant from each can? Well, you want to make sure that you're controlling the experiment. So you want them to get equal amount of energy. And to do that, they should be the same distance apart so that they're both receiving the same amount of radiation. 7, which can receives more light energy from the bulb? So which receives more light energy from the bulb? It doesn't say which one's absorbing more energy from the bulb, so this is a trick question. All right, that means technically the amount of energy coming out of this light that doesn't vary. That doesn't change. So both can receives the same amount of light, but each can will absorb it differently. Okay? So they both receive the same amount of light. All right, if you were to graph this, maybe we'll make the dark can, we'll make the dark can red, and we'll make the light can blue, and we'll sketch. We'll just sketch what would happen over 20 minutes. So over 20 minutes, we're probably going to have, for the light can, or the dark can, we're probably going to peak, and then settle. So it's going to turn on, it heats up, turns off, cools off. But for our light can, it's probably going to not heat up as much, and then when you turn it off, it's going to lose heat faster because it didn't gain as much to begin with as the dark can. Okay. All right, let's get to now. We are in the convection, conduction, radiation, independent practice, and guided practice here. You might want your access point and your practice document open together as their own tabs. Ooh, it's my reference tables. All right, so here we've got the convection, conduction, radiation, guided, and independent practice. Please, for a moment, try out question 1 and 2. Pause the video, and we'll be back. All right, so you've paused it. I even had to take a pause. I need a bit of a breather, right? Time out, water break. I'm sure a lot of you have probably been through quite a bit already if you're watching this and all my videos, which I appreciate you watching my videos. Thank you for subscribing. Thank you for liking. If you even got this far in the video. Oh, I miss you kids. It's going to be sad going all these days not having all of you in class, but I digress. All right, so arrows in the diagram below represent the daytime flow of air over a coastal region. Dun, 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 dun. This looks very similar. So hopefully you either looked at your axis point or jumped back into your notes to find an example. We've got the sun, our heat source. We've got an ocean, the beach. We've got a bunch of arrows here representing convection. All right, so there's your answer. I mean, I think it's going to be important that you look at these pictures more and more and you start to associate them with the vocabulary, and you'll be more likely to understand maybe questions that are more in depth, maybe more challenging. Okay? Down here, we've got which diagram best represents the heat transfer mainly through the process of conduction. So we've got to remember the definition of conduction. It is a transfer of heat through solids. So we have to go through and figure out which one is a solid. No. That's our conduction, that's the fluid. Sun to earth, no, that's radiation. Asthenosphere, it's pointing to the asthenosphere here. So that is a convection cell. It's a very thick fluid, rock-like plastic fluid in a way. This one, atoms vibrating in a metal rod. Right there, metal, okay? That's your solid. All right, go ahead and check out the access points. Dive into your independent practice. Don't forget to check your answers. Feel free to comment below with questions there, or in Google Classroom, hit me up through Jupyter, whatever you want in terms of communicating. And hopefully we have maybe a different venue to communicate through by the end of this week. All right, thank you for watching. I hope it helped. We'll see you later.